Good morning, grade 11s. Today is Thursday, June 16th of 2020. Coronachem, day 50. There's only one more day of teaching left. Really, I might just not even teach tomorrow. We'll see. So this is the review of the mock test I gave you yesterday. I gave you 5 questions. I gave you one more than usual because some of the questions are pretty trivial, or one of them at least. The first question asks,
calculate the number of molecules in a deep breath of air whose volume is 2.5 liters at body temperature 37 degrees Celsius and a pressure of 735 torrs. So PV equals nRT. We're going to solve for N. We'll transpose all the values so that PV over RT gives you N. The pressure is 735 760ths of an atmosphere, because we know there's 760 torr in an atmosphere, which you should memorize. 2.5 liters of air. Here's the gas constants for liter atmospheres, and the temperature in Kelvin, the absolute temperature scale. You have to add 273.15 to the Celsius temperature to get the absolute temperature. You'll see that atmospheres cancel, liters cancel, kelvins cancel. You're left with an answer in moles. This is in the denominator of a denominator, so it becomes a numerator. You have that many moles, forgot to put moles here, of air times an Avogadro's number of molecules per mole gives you that many molecules. After significant figures, you round it to 5.72 times 10 to the 22 molecules. The answer to 1042, I asked you to try to reproduce the answer as homework. So the answer to that question on 1042 is in yesterday's video, day 49, where I explained how much mercury was released by Mount St. Helens per day. 42. Let's have a quick look at it. Yeah, it comes out to 2.88 tons a day, according to the calculation. 2.88 tons of mercury released by Mount St. Helens per day.
The next question is
1045. Let's read that. Which of the following statements best explains why a closed balloon filled with helium gas rises in air? Well, let's explore. Before we look at the answers, let's try to formulate an answer ourselves. When you pump a balloon full of helium, helium atoms have a molar mass of only 4. But if you recall Avogadro's hypothesis, he stated that 1 mole of any gas at standard temperature and pressure, which is 25 degrees Celsius and 0 degrees Celsius and 1 atmosphere of pressure, will have an Avogadro's number of atoms, 6.02 times 10 to the 23. So if a given sample of any gas at the same temperature and pressure has the same number of atoms, then the sample of gas that has lighter atoms will weigh less, even though it occupies the same volume. So there you have the answer to the question. Because the gas has a lower molar mass per unit volume, it's going to have a lower density. Because it has a lower density, it's going to occupy more space per unit weight, or if you prefer it, it'll have less weight per unit space. Point is, if you have a balloon, the balloon will displace more air than it weighs, or the air that it pushes out of the way to form its own volume weighs more than what the balloon weighs, so that causes the balloon to be buoyant. And so helium balloons actually are lighter than air. They float up in air. The same happens with a ship. A ship could be made of metal, but when you put it in the water, it pushes out of the way the equivalent of its weight in water. So if the ship weighs 1,000 tons, it'll push 1,000 tons of water. It'll displace 1,000 tons of water. And so if the ship, as long as the ship can displace more water than it weighs, it'll float. If at some point the ship weighs more than the water that it's displacing, then it'll sink. And that's the concept of buoyancy. In the human body, our density is very close to the density of water. When we take a breath of air, we fill our lungs with air so we increase the volume of our rib cage, so we displace a little bit more water, which means we tend to weigh less than the water that we displace, so we float. When we let the air out of our lungs, we displace less water than what we weigh, so we tend to sink. So we can adjust our buoyancy by breathing air in and out. Fish do this by having a bladder inside of their bodies, which they can inflate or deflate according to their desire, so that they can adjust their buoyancy. So a fish can sit still in the water without floating or sinking, because he adjusts the bladder inside of his body to adjust the volume of his body accordingly to give neutral buoyancies. Submarines do the same thing. They take on water so that the density of the submarine equals to the density of the water that it displaces. Not the density. So the mass of the submarine is equal to the amount of water that it displaces. That's how you achieve neutral buoyancy. Okay, the next question was 45, we did 45. So the answer is C. The balloon is filled with gas of lower density. It displaces more air than it weighs, causing it to be buoyant. The next question is 50. So, the molar mass of a volatile substance was determined by the Dumaville technique described in exercise 1049. The unknown vapor had a mass of 8.846 grams. The volume of the bulb was 354 centimeters cubed, pressure 752 torr, and the temperature 100 degrees Celsius. Calculate the molar mass of the unknown vapor. So we're going to start with PV equals nRT. And we're going to rearrange the equation to solve for the amount of moles. PV over RT is going to give you N. So if I divide both sides by RT, that's how I get that. Okay? RT's cancel, and you get N equals PV over RT. So the pressure is 752 760ths of an atmosphere. The volume is 0.354 liters because you had centimeters cubed, and there's 1,000 centimeters cubed in a liter. 0.082057 liter atmospheres per Kelvin mole is the value of the gas constant, and the temperature is 373.15 Kelvin. So the number of moles you get from that is 1.14. 395, 365 times 10 to the minus 2 moles of gas. Now, the molar mass is calculated by taking the mass of the gas, 0.46 grams, and finding out how many moles you have. You have that right here, 1.14, etc., times 10 to the minus 2, and you get units of grams per mole. That's the units of molar mass. So what you get is 73.954. 0.451 grams per mole. And the molar mass, when you write to the appropriate number of significant figures, is 74 grams per mole. That's 1050. The last question I gave you was 60. Let's have a look at that. Question about partial pressures. So let's do 1060. Mixture containing 2.5 grams each of methane, ethane, and butane is contained in a 2-liter flask at a temperature of 15 degrees Celsius. Calculate the partial pressure of each of gases in the mixture. Calculate the total pressure of the mixture. So, you had 2.5 grams of methane with a molar mass of 12.011 plus 4 times 1.00794. So that gives you 0.1558335 moles of methane. You had 2.5 grams of ethane, C2H6. Oh, sorry, it's ethene. Double check. Yeah, it's ethene. With a molar mass of 2 times 12.011 plus 4 times 1.00794 grams per mole. That gives you 0.089114 moles of ethene. And the last sample was 2.5 grams of C4H10, which is butane. So 4 times 12.011 plus 10 times 1.00794 grams per mole means you're going to have 0.043, 0.11936 moles of butane, C4H10. If you add up all the moles of those gases, the total number of moles of gas is 0.28796, 0084 moles of gas. You just call it gas. So the total pressure is going to be directly related to the total number of moles of gas. It doesn't matter what shape the gas has according to the ideal gas equation. According to the ideal gas law, the chemical composition of the gas is irrelevant. Its contribution to pressure is strictly the function of how many moles of the gas are present. So find out the total moles of gas. That's going to help you find the pressure. So total pressure then is given by P equals nRT, where N is the total amount of gas. So P equals 0.28796, etc. moles times the gas constant. Oh, this equation simplifies to nRT over V, right? Divide V on both sides. So you get 0.082057 liter atmospheres per Kelvin mole. For the gas constant, temperature is 273.15 plus 15, because the experiment was conducted at 15 degrees Celsius. And the total volume is 2 liters. What you get as a total pressure is 3.4 atmospheres after sig figs. It comes out to 3.404368434. I had to round it down because I didn't have room there. So now I'll do the second part, which asks
calculate the partial pressure of each of the gases in the mixture. Calculate the total pressure of the gases in
well,
one.
here's the total pressure. That's part C.
So we did,
Sorry, we did part B first. This is part B. Now part A, I have to finish it. So I have to take the mole fraction of each one of these and divide it by the total amount of moles, 2.287, etc. That's equal to the X. Okay, so for each one I do that. Divide each one by 287, divide this by 287. Use all the full decimals, I'm just abbreviating it for lack of space. That's your mole fraction of each gas. Now the total pressure is 3.4, so the pressure contributed by each gas is equal to the mole fraction. So take these numbers, multiply them by 3.4, and you get the pressure exerted by each gas. So we're going to do that on the next page. So the pressure of the let me just double check something here. 0.155. pressure exerted by methane is equal to the mole fraction of methane times the pressure total. So mole fraction of methane is 0.1558, etc., over 0.28796, etc., times 3.4, which equals 1.8423204. After the correct number of sig figs, you're going to write 1.84 atmospheres. Okay, so there's the partial pressure of methane. Partial pressure of ethene, C2H4, is equal to the mole fraction of ethene times the total pressure. In this case, it equals 0.0891, etc., over 0.28796, etc., times 3.4. After sig figs, you get 1.05 atmospheres. And last one is the partial pressure of butane, C4H10, equals the mole fraction of butane times the total pressure. In this case, it's going to be 0.043, etc., times divided by 0.287, etc., times 3.4. After sig figs, you're going to get 0.509 atmospheres. And these three numbers should add up to 3.04. Or sorry, 3.4, because the partial pressure of each one adds up to the total pressure. That's it for today's mock test. So I'll give you tonight to study it. Tomorrow morning, I'm going to write down the questions for the real test. Obviously, they're going to be similar to what we've been doing. And that test will be due 6 p.m. Friday night. That way it gives me the rest of the weekend to correct the test and then compile a mark. I should have a final mark for you by Tuesday at the latest, because that's when I'll do anyway. And enjoy your summer, and I hope you do very well in life. Let me know how things go. Drop by the school when all this blows over. Hopefully it does blow over soon. I say it wouldn't hurt to say a few prayers, because there are things going on that are probably not 100% upright. I've been calling them into question, and I will continue to do so, because I see things happening that shouldn't be happening, and there's a lot I question. Do the same. Question what goes on around you. If I've taught you anything, it's that. Don't always believe what you see on TV or on the internet. So good luck, and we'll give you the test tomorrow.